Today we have an international visitor coming in from Linköping in Sweden. I first met Alex Gillett when I was... Is it Gillett or Gillett?
Gillett. You got it right the first time.
When I was working in Cambridge in the optoelectronics group doing my postdoc, and Alex was always working in the ultrafast lab, and even though I was the postdoc, I'd be asking him for questions all the time. So he was well ahead of the game all the way back then. He graduated from Cambridge in 2019 and hung around, as he's just said, for a little too long. No, he hung around because he picked up an early career fellowship at Cambridge, which is no small feat, before starting his own independent career in Linköping late last year. Even in his PhD, he was working on excited states and organic semiconductors, but I think this is going to be a little bit more in depth now on the spin-triplet excited states and organic semiconductors. So can everyone please welcome Alex, and the floor is yours.
Thank you very much. Great, thanks for the introduction, Brad, and thanks again for inviting me to come and give a talk here. So yes, as the title suggests, I'm going to be talking about some of our recent work on spin-triplet excited states and organics. So looking a bit at organic light-emitting diodes, a bit at organic photovoltaics, and just running through some fun spectroscopy on these systems. All right, so I think I should have, there we go. So I guess people are probably reasonably familiar with what organic semiconductors are. It's got a couple of introductory slides to get everyone up to speed in case not, and then we'll get on to the data. So yes, organic semiconductors, as you may well know, materials, as the name suggests, they're primarily made from carbon and hydrogen atoms. And, compared to things like silicon, which obviously is very famous over here, they're pretty disordered, quite impure. But despite this, they work pretty well in optoelectronic applications. So, for example, if you have a Samsung Galaxy phone, an Apple iPhone, whatever, you have a little OLED display you're sort of interacting with multiple times a day in your pocket. And again, maybe controversial given where we are, but organic PV has been doing pretty well recently as well. And it's probably not going to compete with silicon or perovskite for large-scale solar applications, but for indoor PV, some niche stuff with flexible solar cells, transparent, building integrated, it could be pretty good. So they're quite nice materials, I think. And one of the things that sets organics apart from most inorganics is the fact that they're excitonic semiconductors. And this basically means that when you photoexcite your organic molecule, due to the kind of quite small dielectric constant, you get a pretty weak screen between the electron and hole, and they form a sort of Coulomb-bound excitonic state with a binding energy on the order of a few hundred millielectron volts. And this generally means the organics are localized on a single molecule, the excitons. If you compare it to something like silicon, the high dielectric constant, you basically photoexcite it, makes free charge carriers. And that's again why silicon works so well in photovoltaics. So these excitonic properties of organics are quite interesting and unusual, and that's what makes them quite special materials, I think. So when you start working with excitonic semiconductors, you have to start thinking about the spin of these excitons. And that comes about because you have, an electron, two electrons, let's say, sitting in your highest top molecular orbital, or your valence band. And their pairs spin antiparallel for an overall spin equals 0. You photoexcite it, and take an electron, move it into the LUMO. You maintain that spin of overall spin of 0, get a first sight single exciton. But what makes things quite interesting is that this electron doesn't have to have spin unparalleled to the ground state electron. It can actually have spin parallel to give an overall spin of 1 from the two spin half electrons. And what this means is that basically you have a spin-triplet excited state, so called because there's 3 different ways you could orient those electron spins to give an overall spin equals 1. And indeed, you can get more exotic excited states like quintets, quartets, whatever, if you have multiple electrons in your system. And what's quite interesting is in most organic materials, you have something called this electron exchange energy here, which is basically the overlap between the electron and hole wave functions. And this can be quite large in molecules which have quite significant overlap of your electron and hole wave functions, shown here by the HOMO and LUMO. And what this means is in organic materials, it depends on the compound, of course, but you're typically looking at an energy output between the singlet and triplet states of on the order of at least half an EV, maybe a bit bigger. And this has some quite significant consequences for how your optoelectronic devices work. And one of these main consequences is the fact that this transition here, taking the electron the spin parallel electron from the LUMO back down to the HOMO, is formally spin forbidden because you can't have 2 electrons spin with the same spin quantum number in the same orbital. And what this means is in the absence of iridium or some kind of heavy metal to give you significant spin-orbit coupling, this process can't happen with photon emission. And this basically means that your spin-triplet states are generally dark states. So they don't really absorb light and they don't emit light very well. And this can have, as we'll see shortly, some important consequences for how photovoltaics and LEDs operate when they're made from organic materials. So kind of start off the talk, I like to talk a bit about organic photovoltaics. And they've been doing pretty well recently. If you kept up with the field, they have efficiencies, at least on the lab scale, for about 21% now or so, which is, kind of putting them up in the big leagues with silicon and perovskites, which are hitting 25%, maybe a bit more, depending on your module. One of the things that's quite surprising that organics work so well, given the fact they're pretty bad pretty impure disordered semiconductors. One of the questions I'm interested in as well, they're doing pretty good, 21% efficiencies, but why aren't they better? Why aren't we getting up to 25% like silicon and perovskites? And the question I'm sort of interested in is, are these spin-triplet excited states involved somehow and why they aren't as efficient as they could be? And to sort of explore this a bit further, we can talk about voltage loss in our solar cells. And this is basically the energy loss between the optical bandgap of your material, defined by Eg, and the energy of the extracted charges, which is defined by the open circuit voltage. We can break this down a little bit more. So we have sort of two key factors which control your energy losses. Somewhat unique to organics, you have energy loss associated with charge generation. And this is based on energy you need to get that exon apart, split it, and make a charge transfer state. And then sort of our good organic solar cells made from so-called non-Fullerian electron acceptors, we've done, by organic standards, pretty well at minimizing this. So we're down to, depending on whose calculations or measurements of the HOMO LUMO you believe, on the order of 100 millielectron volts or so, which is still there, but it's definitely improved from where it was quite a few years ago with Fullerians. Where we get into now with charge recombination losses, we have a radiative non-radiative component, which all the silicon guys are probably quite familiar with. So our radiative recombination is included in the Shockley-Queisser model. It's unavoidable in all solar cells, and constitutes on the order of maybe 300 millielectron volts or millivolts or so. When we look at our non-radiative voltage losses, organic's not doing so well. We have sort of a non-radiative voltage loss on the order of, in the best cells, 200 millivolts or something like this. And conveniently, this can be directly calculated from the natural log reciprocal of the electroluminescence quantum yield of our materials. So basically, you take your organic solar cell, you run it as an organic light emitting diode in effect, and see how efficiently it emits light. And using some maths, we can get back from that number to how big this non-radiative voltage loss contribution is. So basically, what's happening is organics don't have much radiative combination, and that's why they're bad, effectively, or relatively bad. So, these are just some representative numbers. If we look at gallium arsenide, which I guess is probably as close to ideal semiconductors as we're going to get, we're looking at non-radiative voltage loss, 300 millivolts or so, and a very small contribution from the non-radiative component, which shows it's quite a good emitter. Things like crystalline silicon and perovskites, a little worse, but still pretty nice. Maybe non-radiative losses on the order of 100 millivolts or so. And then we compare organics down here, which have a total of energy loss of about half an EV, which is significantly bigger than the others. And a big fraction of that, at least, is due to non-radiative recombination. So the question, why might triplets be a problem in organic solar cells? And that comes back to what I mentioned before about the electron exchange energy. So we've been quite good at getting this energy gap down between the singlet exciton state and the charge transfer state to on the order of 100 millielectron volts, depending on who you want to believe. That's great. That really minimizes our energy loss and charge generation. But then with our organics, we have quite a large singlet triplet energy gap. And this means you have a lower lying triplet state, let's say on the order of half an EV below the singlet. And we know that state is dark. And the problem with this now is we have, through our sort of charge generation, through the CT state of free charges, and the recombination back into the triplet CT state or singlet and so on, we have quite efficient spin mixing channel. So we can efficiently populate the spin triplet charge transfer state. And now there's sort of a spin allowed back charge transfer process which takes an electron or something, puts it back onto the lowest energy triplet, molecular triplet in your system, gets stuck there. And generally, there's not really much you can do about that. It's thermodynamically favorable because the triplet is probably the lowest energy molecular state in your system. So you kind of end up forming these triplet exons by charge recombination. They sit there and they probably decay non-radiatively because they aren't bright states. And when we have the sort of energetic landscape like we see here, it's very, very difficult to block recombinations to this triplet state. And if you do that, you may have a problem. So the question becomes, okay, we at least theoretically think there's a way to populate triplet excitons, but why should we care about them? What effect might it be having on our device performance? Well, I showed this equation earlier, which is basically relating the magnitude of this non-radiative voltage loss in our device to the electroluminescence quantum efficiency of our PV device run as a light emitting diode under forward bias. Well, our OPV device running on a forward bias is basically just an OLED. So, and the equations which could govern the luminescence continuity of your OLED are quite well known. So, for example, this is one of the main equations in the field. So we see that our electroluminescence quantum yield of our OPV device is a function of a few factors. So things like charge balance in your device, so ensuring you have an equal number of electron holes in your active layer to recombine, that could be important. Light-out coupling, so in an OLED, maybe you're getting 20-30% light-out coupling efficiency, so that can be a significant loss. The sort of two of the main factors I think we have potentially more control over, or we should care about more because they're bigger at this stage, is the photoluminescence yield, the intrinsic photoluminescence yield of the singlet states in your device, which kind of provides like an upper limit to how efficient your OLED can be. And also this chi factor, which is basically the fraction of these electron hole recombination events that can result in photon emission. So if electron holes come together, what's the chance they form a spin singlet state, which can then decay radiatively and give you some light out? So one of the sort of key things that's known in the OLED field is if you have a spin uncorrelated electron hole or two electrons, which you inject into your device, when they meet, due to spin statistics, there's one way they can orient their spins to give an overall spin of 0, so your bright spin singlet configuration, or there's 3 ways they can sort of recombine to give an overall spin of 1, which is your dark spin triplet combination. And what this kind of means is that in the first approximation, just through your charges and OPV kind of recombining, 3 times out of 4 they're going to form a triplet configuration and therefore be dark. And I think this is quite an important thing because with organic solar cells with a band gap on the order of 900 nanometers or something like that, they're emitting at about a micron. And due to the energy gap law, it's really tough to increase the PLQI of your materials because non-radiative decay is so dominant at these wavelengths. So I think, at least my opinion, is if we want to really improve the EL yield of our devices, a sort of, not say easy win, but a potential big win, is looking at improving the or targeting the triplet combination. Can we turn it off? Can we mitigate it? Something like that. And I think, this is kind of a key crux of what I'm interested in. Is there ways of understanding triplet combination and turning it off or mitigating it? So one of the things we do a lot, so at least back in Cambridge when I was there, is transient absorbance spectroscopy. And this is some data taken from my publication in Nature a few years ago now. But what we did, amongst other things, is we took a combination of this electron-donating polymer called PM6 and this electron-acceptable molecule called Y6, which is sort of, at the time, was a very new, but is now a kind of very classic benchmark system in the field. So we did our transient absorbance spectroscopy, which, if you aren't familiar with the technique, is kind of just like time-resolved UV-Vis. So rather than looking at like the ground state absorptions of your material, you're looking at the excited state absorptions instead. And we're tracking how those change with time. You can build up kind of like a fingerprint or a sort of movie of how your molecule is behaving after it absorbs a photon and what's going on. So we took our mixture of PM6 and Y6, which forms the basis of a fairly nice organic solar cell, and we excited at 800 nanometers, which is just exciting our electron acceptor component here, this Y6, because the PM6 has a wider band gap, doesn't absorb light in the this near-infrared region. So what we did, we pumped our molecule at our blend at 800 nanometers, and after a few hundred femtoseconds after excitation, we have the spectrum in the near-infrared that looks like this blue curve here. And this is basically a signature of excitons forming on Y6. So we excite it, we make single excitons, it makes sense. What we find is that with time, as we go from blue through to these kind of beigey, green, yellow colors, we see a quenching of the absorption band at 1550 nanometers, and it goes away. And that's just due to hole transfer from this molecule to the polymer, basically quenching the excitons. And indeed, there's a polaronic absorption of this polymer. I'm not showing it, but it's somewhere down here at about 950 nanometers or so. What we found is quite interesting is over sort of hundreds of picoseconds and nanosecond timescales, you get this kind of yellow bump forming here at about 1450 nanometers. And if you compare it to the sensitized Y6 film, so we basically mix Y6 with a platinum porphyrin just to dump a load of triplets onto it, we get this dotted red spectrum here, which is a very, very close match to the yellow little bump we see there. And what we think this is telling us is that, as their charges are recombining, they're forming a new species, and this seems to match the excited state absorption signature of the triplet exciton located on this Y6 component. So that was quite interesting. And what we wanted to do more was to try and work out how are these triplets being formed. And what we can do is something called a fluence series, where basically we look at how the kinetics of our sample, the behavior changes as you increase the laser power. So you're basically making more excitons, more charges. What does that change? And what we found was quite interesting. So we took a kinetic from about 1450 nanometers, which is roughly at the peak of this triplet absorption band of Y6, There was early times it does overlap with this single exon absorption band here in the going off more towards 1500 nanometers. So what we see in the first sort of, let's say, 10 picoseconds, the kinetics kind of match, and that's basically just showing that you have quenching of the excitons by Hall transfer from Y6 to the polymer. That's fine. But what we found at later times is quite interesting. So at a relatively low fluence, I think this works out to be approximately 3 suns, which is getting towards the limit of what we can probe in TA. What we find is that we get quenching of the excitons by Hall transfer, and over sort of hundreds of picoseconds and nanosecond timescale, get this little bump forming. And this is basically just a signature of these triplet excitons growing in. When we increase the laser power, you see that this bump gets more prominent relative to this initial point of normalization, which should be the same for all the samples, for all the fluences, and gets more intense more quickly, basically. And what this really points to is a so-called non-germinate mechanism for this triplet formation. What it's saying is that we excite our material, make some singlet excitons, to do some kind of charge transfer, make a CT state, make free charges. And eventually, through that sort of spin-statistical recombination, we can populate the spin-triplet charge transfer state, and then that recombines to the molecular triplet on your Y6 material. And why this should be fluence dependent is because the harder you pump your material, the more free charges you create. And the kind of increased free charge density in the film means they're more likely to bump into each other more quickly, and then they're more likely to therefore recombine and make a triplet. So this kind of fluence-dependent mechanism we see here is indicates a non-germinate process, and we found generally is the dominant triplet formation mechanism in a good solar cell. So in a bad one, you can get like a germinate one where you get trapped in the CT state, do intersystem crossing to the triplet and stuff, or you can just do direct intersystem crossing from undissociated singlets. But in one that works well, this is one we see. So we can see the triplets in our PM6Y6 blend, but the question is, what sort of impact are they having on our device performance? So to begin with, we wanted to quantify the triplet formation. So what we did, we basically fitted a kinetic model for that data. I haven't shown you because it's just lots of equations and graphs and lines overlapping, but effectively it's a function of a global fit, just tracking how this triplet forms compared to the whole polaron, which is more towards 9 nanometers, how that decays. So what we're saying is basically the rate of change of our triplet population should be equal to the decrease in the polaron population times by some factor which says what fraction are going to triplets. And then this kind of annihilation term, which is basically the triplet charge annihilation break constant multiplied by the density of triplets and charges in your film. So I won't show you the fitting just because just trust me, hopefully it's in the papers, hopefully you believe it looks okay. Depending on what values you take for absorption cross sections and so on, we can estimate on the order of 90% of the charges recombine to make triplets in our PM6Y6 blend, which is a very, very high factor and was potentially quite surprising. I should point out we've done some other blends and other parameters, and we typically get on the order of 80-ish, 90%. So we're reasonably confident that this is a correct-ish number, and it's not just, massively overestimated. So we get this alpha, which is the fraction of the charges that make triplets, 90%. Remember this chi term from our equation for the non-rated voltage loss, for the EL efficiency of the OLED, which then links non-rated voltage loss. That should be 1 minus alpha, so what fraction of combination events can lead to photon emission? If 9% make triplets and can't make photons in theory, 1 minus that. Yeah, makes sense. So we say that chi is 0.1. Put this into our equation for the EL quantum yields. Well, if chi is 0.1, we decrease that EL by a factor of 10 compared to the maximum we could possibly get out of it. Plug that back in, this factor of 10 difference, into our equation for non-rated voltage loss. And what you find is your open circuit voltage of your organic solar cell, if you have a really significant triplet combination, is reduced by on the order of 60 millivolts or so. And if you remember, we're potentially about, in non-rated terms, 100 millivolts, 100 a little bit more off from being at a similar level to silicon and perovskites. What we're kind of saying then is actually the triplets are half of your problem, give or take. The other half is probably due to the low intrinsic luminescence yield of our near-infrared molecules, which is also harder to sort of deal with. So I think the take-home message from this is, if you want to make your solar cell better, triplets are really important to consider. And if you can get rid of them effectively, you stand to gain quite a lot of VOC, which can take you from 20%, 22 or something better at least. So I showed you some data from that combination of this polymer PM6 and this electron receptor Y6. But working with some of our collaborators, Quinn Wynn's group in UNSW from Gal's group in Linköping, they kind of provide us with lots of different molecules. So we have 3 different electron donating polymers, or 4 even, sorry. So here, 2 different fluorinations here and this one, and a range of different electron acceptors. So we sort of blended them together and made some devices. They, for devices at the time, worked fairly well. And we did the same measurements. Can we see triplets forming from transient absorption? So what we found is most of them did indeed show similar things to that PM6Y6 combination I showed you before. But a couple of them, this PTB7 polymer with this IEICO acceptor. So it's going to be this polymer with some of these acceptors. We did the fluent series, we just couldn't see triplets forming. And that was quite interesting because we generally in fullerenes you see a lot of triplets. In most NFA systems we found a lot of triplets, but these two just didn't seem to show a lot. So, okay, that's fun. Should we try and understand that then? Add some water quickly. So we worked with our theory collaborators in the group of David Belgian in Belgium. And they did some very nice calculations to help us understand why this might be the case. So I'm showing it to you for one system, this PTB7 with this IEICO2F acceptor. We ran it on the 4F, also didn't show triplets, and a lot of the ones that did show triplets. And we found generally, I mean, it's just a model, but it seemed to be in quite good agreement with the experimental results, so we consider it could be a possible explanation, let's say. So what our collaborators found is if you have your molecular states here on your non-following acceptor, so singlets and triplets, and your charge transfer states, or charge transfer excitons, as I've called them here. If they have the right symmetry, close energetic alignment, strong coupling, you can get a kind of mixing of their wave functions. It's a kind of hybridization interaction. What we find is basically is that the CT state gets a little admixture of the singlet exciton, and vice versa for the singlet exciton gets a bit of CT state mixed in. And in kind of simple molecular orbital pictures from undergraduate chemistry, you get one gets a bit stabilized, one gets a bit destabilized. And that actually, that actually leads to kind of vector intensity borrowing, which can make your CT state a bit brighter, which is being explored quite a lot in the field. That's what it is. What we also found that people hadn't considered before is that your molecular triplet exciton, you have the same conditions, same things apply. You can also mix with your charge transfer triplet state. What we find is a slight destabilization of the charge transfer triplet state as a high energy state through an admixture of a bit of the triplet wave function. What we find is that kind of could potentially create a kind of energetic inversion of the singlet and triplet. So your triplet CT state becomes slightly higher in energy than your singlet. But that's interesting, but why might that block triplets from forming? So what they also did, they calculated the energy of your spin singlet by the squares and your triangles, your spin triplet charge transfer states as a function of the separation of the donor acceptor. So based on their model, you have your donor acceptor that kind of held at the pi-second distance, and then you sort of pull them apart and see what happens first to your energy of your charge transfer states, but also the rate of this back charge transfer process, which I'll get onto in a second. So with your singlet charge transfer states at a relatively larger electron separation, so larger distance between the donor and acceptor, you have a higher energy, which makes sense because the Coulomb interaction is less stabilizing your electron hole pair less. And as you bring them closer together, you get a decrease in your energy, which again makes sense because as you get things closer, the Coulomb interaction is stronger and it stabilizes it. So that kind of makes sense. What they found was quite weird was with the triplet state, these triangles here. So they found that, at a larger electron hole separation, you get a small positive exchange energy, which is what you'd expect, due to kind of weak wave function overlap. But as you sort of bring the molecules closer together in the model, the sort of gradient becomes much shallower than for the singlet. It bottoms out, a little bit back from, let's say, the interface. And it even has a little uptick here where it gets destabilized as it approaches the interface. This is quite unusual. So what they think was happening, basically, as you bring your molecules closer together, the hybridization kicks in because you have strong electronic coupling. And this sort of creates a sort of distance-dependent effect on the CT state energy of especially the triplet. So it gets slightly destabilized as you decrease the distance. And what that kind of means in reality probably is that your electron hole pair, the most stable configuration is not to necessarily sit right at the interface, but maybe sit a little bit back from the interface. Maybe at a molecule further back or, in some kind of regime with more disorder or greater pi-second distance at the interface. This has quite a big effect on the sort of electron transfer rate that goes from the triplet charge transfer state through to the molecular triplet. So as you'd expect, it has a kind of roughly exponential dependence on distance due to wave function overlap of the initial and final states. And what we find basically as you go back from the interface, you can really decrease the rate of this back charge transfer step that takes from the triplet CT state to the molecular triplet. Coming about on the order, on the order of magnitude, maybe even more. And what that kind of could do is, if your rate of reseparation of your charge transfer state, we think it's probably on the order of 10 to 12 or something inverse seconds. It kind of makes that outcompete the back charge transfer process potentially. And that can mean that the electron hole pair just reseparates rather than reforming a molecular triplet state. And that could, in theory, reduce or even block your triplet combination. So that's obviously just, not to just a model, let's say, but it also, we calculate this in many, many systems. And it seems to have quite good empirical agreement with what the system saw triplets in versus the ones we didn't. So that could be a potential route as to how you can block your triplet formation. So that was, quite a fun project. We had some interesting design rules you could potentially use, but I think in reality, it kind of comes down to luck. You just have the right combination of donor acceptor, the right morphology of the interface. There's not really much control. It's quite serendipitous. And that is tough to implement, let's say, in a real device. You kind of have to get lucky with the right combination. And we found a lot of these sort of PM6, Y, whatever systems still show triplets. So clearly that combination, which gives the best devices, isn't the one which has block triplet formation. So yeah, kind of stuck there. So we started thinking of ways where, okay, if the triplets are going to form, can we mitigate it at least a little bit, so make the impact less severe on the VOC of your device? So one thing we came across, kind of, I guess, inspired by the OLED world, where, until fairly, well, I think even still now, your blue OLEDs are made with triplet annihilation materials, because iridium phosphors aren't good in the blue and TADFs aren't stable, basically. So we kind of thought, well, okay, if it's good enough for a blue OLED, is it good enough for OPVs? And I guess, as you may be familiar from the singlet fission world, TTA is just the opposite process, basically. So what kind of happens is, two triplets can bump into each other, depending on the energies of the singlet, triplet, and quintet triplet pair states, and blah, blah, blah. You can get lucky if everything aligns well, and then you can basically take your two triplet excitons, and in the best case, you can make one singlet exciton from it and one singlet ground state. So you can, from spin statistics, if, again, you get lucky, the two triplets make one singlet, you kind of see that this will increase our chi factor from 0.25, predicted by the kind of, the spin statistics, up to 0.625. So taking the 75% triplets, half of them make singlets again, so 37.5, and yeah, add them together. So the question was, okay, that's interesting, and can we make this work in an OPV and recycle our triplets to at least get something back out of them? And this is part of a paper we did in Advanced Energy Materials from a couple of years ago now. So what we found actually, probably through luck, is we found this derivative of a Y6 material. So this is called Y11. Very, very similar to the Y6 I showed you before, except we replaced in this center bit here the benzothiazole for benzotriazole and added a side chain on. And this can change properties surprisingly quite a lot. One thing that's quite unusual is we actually find evidence in the neat Y11 film for triplet annihilation. So for example, we just nanosecond TA measurements over here on the left. Looking, it's a couple nanoseconds here in the dark blue through to yellowy lime green, which is a microsecond or so. So we looked at the sensitized triplet spectrum. We found that Y11 actually makes quite a lot of triplets just in the neat film. You photoexcite it, you wait a few nanoseconds, and all that's left is triplets. As you can see by the very nice match between the sensitized spectrum and this spectrum we see in the nanosecond TA. So what we're doing, basically, we're exciting it, make some triplets. We estimate maybe 5% or so in system crossing yield, but yeah, something like that. Then what we found actually is this really unusual, very, very strong dependence on the triplet lifetime of fluence. The triplet lifetime of fluence, excuse me. So we have low fluence here in blue, going up to red, which is quite high fluence. And what we find as we increase the fluence, we get a really drastic shortening of the triplet lifetime. So they decay, within even 100 nanoseconds at high fluence. So what we did, we fitted this, Lucy Hart, the student working on this, she fitted this with this model here, which basically says the rate of change of triplet population density is a function of monomolecular triplet decay and triplet annihilation, this kind of gamma n squared term. So you can fit that, which is the black dotted black lines. And indeed, actually, you do need this quite short monomolecular triplet lifetime to fit this. Otherwise, the TTA itself cannot predict the decay quick enough. And this number, about 60 nanoseconds, becomes important later, but I'll get back to that. So what we think was happening from fitting of our models is basically we photoexcite, we make some triplets, and then they can do triplet annihilation. And in theory, you should get some light out, right? That's what we saw. So this is just transient absorption, so you don't measure luminescence. We couldn't see that here. But at least this data gave an initial indication maybe there's some TTA going on. So as I mentioned, TTA should, in theory, repopulate singlet states, and you should be able to get light out from those singlet states, all being well. So what we did is some transient PL spectroscopy using our very sensitive ICC detector in Cambridge. And what we found was quite curious. So if you ignore this kind of instrument response, where everything kind of just looks the same because our detector isn't super fast, what you find is you do indeed see some delay fluorescence coming from this Y11 film, which again is quite unusual. I wouldn't have expected the material would be a good TDA emitter, but there we go. We did a fluence series, so we increased the laser power from 12 microwatts up to 50. What we find is actually relative to this point of normalization, the kind of delay fluorescence gets relatively more intense. And that's kind of fits with the idea of TTA, right? Because if you pump it harder, you make more triplets, you have a higher triplet density, and therefore more likely to get TTA rather than monomolecular decay and so on, get some delay fluorescence out. So that's, I mean, between our TA and our transient PL, we thought probably we had some TTA going on in this Y11 material. And yeah, I've got a slightly bold claim at the top, and I'll explain why in a second, but Rubrine is thought of as being like the archetypal TTA material in the organic field. As I'll show you in a second, the numbers we get out imply that Y11 actually is a better, quote-unquote, TTA material than Rubrine. So again, we did some transient absorption. This is the spectrum over here. Looks very, very similar to what I showed you before for the PM6Y6 combination. And this is just our PM6Y11 blend. So we excite it, you get an absorption of about 1550 excitons on Y11. That decays away. And you get this quite intense triplet band forming at about 1400 nanometers or so. Again, looks very much like the Sensei spectrum, so we're pretty sure that's triplets. We go to our fluence series again over here. Well, we get something that's quite unusual. So if we, by first glance, looks quite unusual. So blue, dark blue is our lowest fluence, and this sort of lime greeny color is our highest fluence. So we get an overlap of the first sort of 10 picoseconds, which is just the excitons being quenched. And then we find is actually, it almost looks like the lowest fluence here has the sharpest rise and the highest peak relative to this point of normalization. And it kind of almost looks like the low fluence is forming more triplets than the higher fluence. Like you see, as we increase the fluence, this peak gets relatively less intense. And that was really, really weird. Then we thought about it a bit. And if you look in this little bit here, you can see actually, at least at the start, you kind of get the trend you expect, which is lower fluence has a less intense triplet peak, and then higher fluence gets more. So that was kind of strange. And what we thought was kind of happening, we fitted again with similar kinetic models to before. We tried triplet charge annihilation, a mix of TTA and TCA, and then TTA by itself. The only one that kind of worked was TTA. What we think is basically going on is that the triplet annihilation in this Y11 material is the rate constant is so high that it just, as soon as your triplet density gets pretty high in the highest fluence, it just quenches them, right? TTA really, really quickly. I mean, again, with the caveat cross sections and whatever, we can sort of estimate a TTA rate constant for this PM6Y11 blend, and we get something on the order of, let's say, 10 to the negative 10 centimeter cubed inverse seconds. And why I say it's better than Rubrine is that, a similar measurement done with TA to look at the TTA rate constant of Rubrine gives something on the order of 10 to the minus 13. So, I mean, there's obviously errors associated with calculating exciton densities through the cross section and so on. But we have 3 orders of magnitude difference, which I think is probably more than any errors in that kind of calculation. So it seems like this Y11 material is actually pretty good at TTA, which is, I think, quite fun. So then, this is work done by Lucy Hart. This is her modeling. She's way better at maths than I am, so yeah, I hand this bit over to her, basically. But basically what she did is she ran some rate equations and worked out what are the potential benefits to open circuit voltages from triplet annihilation. We get a couple of color plots. This one on the left is kind of the optimistic scenario, or optimistic for VOC. It's basically saying you form a triplet, it does TTA, goes back to the singlet, and every single one of those singlets that reforms emits. No more charge transfer. Probably not realistic, but it's one extreme, let's say. So she ran from some maths and basically got an equation out like this, where omega is a fraction of triplets that make singlets again, so maximizes 0.5, so one triplet makes a singlet, so 2 triplets make a singlet. And alpha is your fraction of recombination that goes via the triplet state. And what she basically found that, again, in this kind of unrealistic scenario at least, if you have a lot of triplets forming, so a very high triplet yield, a pretty efficient TTA, you could in theory gain by 50, 60 millivolts or so of VOC, which is quite a lot. Of course, when we go to the pessimistic scenario for VOC, we say that we make our triplets, they do TTA, they make a singlet, and then they infinitely recycle around the loop of make charges, make triplets, lose half of them, make singlets again, and so on. So the reality is we're probably sitting somewhere in between the two. It's very hard to know exactly where we are, but this is the pessimistic case at least. So we see that basically we have, again, a high triplet recombination fraction, efficient TTA, we may be gaining 20 millivolts or so. So like less good, which is to be expected because you're losing one excitation every single time you do the cycle. Nonetheless, it's still, people in the perovskite world are fighting like tooth and nail for like tens of millivolts of VOC. So it's worth considering for sure, especially if organics ever get to that point where we need a few tens of millivolts of VOC. Looking at TTA, probably somewhere lies in the middle of this, could be a valid tactic if we can't stop the strips from forming. So what is happening in our PM6Y11 blend? So it's somewhat disappointing. We ran through all the rate equations and stuff, or Lucy did, I should say. We used some sensible parameters, let's say, from charge combination before 3/4 triplets, such as spin statistics, and some sensible things for the polar density at once and illumination and the bimolecular recombination rate constants taken from this paper, I think from James Durrant's group over here. So we have our estimated TTA rate constant for Y11, which is tends to be the order 10 to the minus 10. And that now becomes quite important on very short monomolecular triplet lifetime, which was quite surprising when we measured it for a few different Y-series receptors, and some other groups have it well, and they also find a very short lifetime. So I think it's probably real. What we have here is under the heat map. This shows on the color scale the fractionation of triplet decay that goes via TTA. So going from nothing, which is dark blue, up to lime green yellow, which is a lot. So we have the imported parameters, which is our triplet lifetime. So if the triplets live longer, there's more chance they'll undergo TTA rather than monomolecular decay. And our triplet annihilation rate constant. So the higher this is, the more likely they will do TTA, obviously. Taking a sort of sensible bimolecular recombination rate constant here, we find that we have a very good TTA rate constant, which is nice. So that could, in theory, get us up to this yellow region, which is where we want to be. But actually, our triplet lifetime is just too short. What that means in the once-and excitation conditions, basically, your triplets will just decay monomolecularly rather than doing TTA. And that's the difference with TAS, where we're working at several suns, where the density is then high enough to get TTA. We just don't have that density in the one sun. So it's a somewhat sad conclusion, I guess, to the paper. We'd have loved to have shown that, this is happening and was effective, but at least gives us some kind of parameter space to work with, or what we want to aim for to get TTA to be useful. I think the main thing is a long enough triplet exon lifetime. So on the order of a microsecond probably is good, and that will put you somewhere up, like in this region here. You have to be careful if the triplets live too long, they can start to do sort of, superoxide formation, all these sorts of things. So you kind of want to balance that lifetime to get some TTA while not having too many triplets, which then give you degradation. As a little teaser for some unpublished data, which probably should get published soon, done from a student I was supervising in Cambridge, Darcy Johnson. And she basically, we went back to Rubin. I say crapping on Rubin a bit, saying our material is better, but actually Rubin, at the end of the day, is quite a nice TTA material. So what we did is, this is all unpublished, I won't go into too much detail, but basically we put our Rubin into our PM6Y6 system. And what we find via TAS and some other data is basically when you put Rubin in, you quench your triplets in Y6. So we think what's kind of happening is basically we make some excitons in our PM6Y6 system, make some CT states, go to free charges, triplets, so on. Then we think we can transfer them quite effectively over to the triplets on Rubin. And from there we get TTA, and then they can probably fret over to PM6 and the cycle begins again. And working with Janine Gruner, who's at the time in Würzburg, but now was in Cambridge and now has gone on to Oxford, she did some photoluminescence detected magnetic resonance measurements, or PLDMR. Without getting into too much detail, basically we're just exciting material and looking how the PL of the sample changes as we sweep the magnetic field in the presence of microwaves that are resonant with the spin transition of the triplet state. We excite only Y6, and we have detection only of the CT states and Y6, so only the near-infrared PL. And what we find to support this mechanism is that basically when you add in Rubin, which is this green spectrum here, into PM6Y6, you basically find that the Rubin starts contributing or mediating, the Rubin triplet, starts mediating the PL of our blend. And this is not from Rubin PL, it's only from the CT states or singlets on Y6. So having the triplets in there directly mediates the luminescence going from triplet states. Thought it was quite a fun story, and that's hopefully something we'll have published fairly soon. Right, I've probably got another 15 minutes or so. So with that, I wanted to change gear and move over to the OLED side of things. So as I guess I probably more than alluded to before, triplets are important for OPV. But I guess kind of the original place they are considered to be a problem was in organic light emitting diodes. That's because when you sort of electrically excite your organic semiconductor, through the spin statistics, you get 75% triplet excitons, 25% singlet. You can get light out of the singlet, that's good. But the triplets, in just a simple fluorescence device, are just lost to heat. They just decay non-radiatively. You don't get any light out from them. But that's quite a severe limit on your efficiency of your internal quantum efficiency of your OLED device. So people have come around to a few different tactics. TTA, phosphorescence, another one, and one that has become prominent maybe in the last, almost probably coming up to 15 years, which is kind of scary. It's something called thermally activated delayed fluorescence. And that's the idea if you basically get a molecule, like this archetypal 4CZ-IPN, so-called because you have 4 carbazoles around the outside and this diazole in the middle. There's a diazole, the dicyanobenzene, whatever it's called. I haven't been a chemist in quite a few years. Yes, if you're making an excited state with charge transfer character, you minimize the overlap of the electron hole wave functions, because the HOMOs get stuck on the carbazoles around the outside, and the LUMA gets stuck on the acceptor in the middle. What you do from that is get a small electron exchange energy, and then you make your singlet triplet energy gap small, which let's say small is on the order of 100 millivolts or less. And then just through ambient thermal energy, you can get a thermal up conversion kind of process, where you do reverse intersystem crossing assisted by thermal energy from the triplet state to the singlet, and then you can get light out, which is good. And in the best case, you can basically get all the triplets to go back to singlets and get an internal quantum efficiency following electrical excitation of 100%. So this in theory solves our spin problem in OLEDs. In reality, it's become quite difficult to implement these materials due to stability, color purity, that sort of thing. But in theory, it's quite a nice, elegant solution. So as I mentioned before, color purity is quite a big consideration in the OLED field. The idea being if you have a very, very broad emission bandwidth, like from this 4CZ-IPN I showed you before, when you want to have an OLED display with a very, very good color purity, very, very well-defined colors for each of the red, green, and blue pixels, effectively you have to use some kind of color filter to basically throw away all the light you don't want and just isolate the little bit that you do want. You're a very, very broad spectrum like this, you end up throwing away tons of the lights, and your efficiency just goes really low because you're just letting through this tiny little bit, let's say around 520 nanometers for green pixels. So one of the sort of solutions that was come up with to sort of improve on this color purity issue was the development of so-called multiple resonance TADFs. I don't know where the name came from. Well, it's done by Hatakama back in 2016. He obviously coined that. Some kind of, I'm not sure I fully understand where it comes from, but effectively what happens is that by having these electron poor boron atoms in your structure and electron-rich nitrogens, you set up some kind of short-range charge transfer state. So rather than having sort of electron donating and accepting groups on your molecule, you have atoms instead. This allows you to make sort of flat planar molecules, like this very archetypal Dabner-1 material. And what happens then is you basically, due to the fact they're plain and rigid, you get very, very nice sharp emission, which you can see here from this nice blue peak from Dabner-1. But also the ability to have a small singlet triplet energy gap by localizing the HOMO LUMA on alternating atoms. And indeed, if you calculate this, not just taking this kind of schematic and actually do the DFT, you do get something vaguely looks like this with, LUMA located more on the boron in the center and on alternating atoms, and then, the HOMO more on the nitrogens and so on. So you can kind of, in a way, have your cake and eat it. You can get TADF, but also narrow emission, which is very desirable for OLEDs. But for me personally, I've always found these molecules, how they work, a bit of a mystery in terms of the detailed spin physics. They kind of just, somewhat better than others, of course, but they kind of work. But I wouldn't say anyone really has a full understanding of what's really going on. But by this, what I mean is, well, in your molecule, you have 3 triplet sublevels. They should, in theory, couple differently to the singlet state, depending on the spin-orbit coupling matrix elements. What's going on with those? We know vibrations are very important for driving the mixing between these states, or mixing with other triplet states and so on. Well, what's happening with those vibrations? And, what I think is quite important is I've seen for that Dabner-1 material, maybe 3 papers now where people have said, we think this is the mechanism of how it works, and they're all different. Like, not to be mean to theorists, but I think theory can only tell you so much, and you have to experimentally back up these predictions to show that your mechanism is correct. So one of the things they wanted to do was, well, theorists can predict something, but can we verify experimentally to, show that there's some truth behind it. Okay, so we have worked with a group of Jan and Olivia in Namur in Belgium, and what they wanted to do was basically, calculate the intersystem crossing of these materials and work out what's going on. So they took, spin-orbit coupling matrix element between the singlet state and the triplet sublevels, and they looked at the spin-orbit coupling, which is basically a combination of your static from the kind of molecular symmetry, so the molecule's not vibrating, and just how those singlet triplets couple just in that static picture, and a contribution that comes from the vibrations, which can basically break symmetry and drive spin orbit coupling between the different sublevels. What they think is the population, well, what's true is the population is of these triplet sublevels should be directly proportional to the magnitude squared of this spin orbit coupling matrix element. So they did some calculations on analyzed Davlin-1 material. What they found basically is that in this kind of static picture, symmetry only allows coupling into the TZ sublevel. When you add in vibrations, you actually get quite strong coupling of the TY sublevel with a little bit extra into TZ, nothing into TX. So they calculated the size of spin orbit coupling matrix elements. You run through a bit of maths, and basically what you predict is that this molecule, most driven by vibrations, should have a dominant coupling into the TY sublevel, a little bit into TZ, and nothing into TX. They can go a little bit further and sort of calculate in a sort of mode resolved way the different vibrational contributions of spin orbit coupling. So you calculate all the molecular normal modes of your molecule and see, as you translate along those molecular coordinates, how is this modulating the spin orbit coupling matrix element. What they found for the coupling of the TY, which I think is the most important one, there's a cluster of modes sort of around, 600, 700, 800 wave numbers, which seem to be ones that have the largest impact on the spin orbit coupling as they twist and vibrate. So their kind of prediction was that this molecule should have mostly vibronic driven intersystem crossing, and it should be dominated by modes around lower frequency 600, 800 wave numbers. So one of the experimental toolkits we have to experimentally determine our vibrational couplings is something called impulsive vibrational spectroscopy. It's just a fancy name for doing transient absorption with a very, very fast excitation pulse. And basically, if the excitation pulse is shorter than the period of vibrational modes, you can coherently excite them. So you go from the ground to the excited state potential energy surface, and your molecules oscillate, at least before they damp, in phase with each other. And then you get some kind of vibrational contribution on your TA data. So to use an analogy, it's like taking a hammer and whacking a bell with a very, very short, sharp smack, and it kind of oscillates and vibrates in phase at least for a short period of time. And so show you what you can get out of that. This is just P3HT, very boring, or classical polymer, let's say. You get a transient absorption kinetic like this here. And what you see, this isn't noise on top of the data after our coherent artifact. It's kind of these oscillations, right? These kind of periodic, spikes. You can basically extract that, Fourier transform it, and you get some kind of, at least in this case, a spectrum that matches the ground state Raman spectrum. So it's basically showing that these vibrational modes are strongly coupled to the excited state, modulating the electron density. If you excite with a very, very short pulse, you can currently excite them and see evidence in the TA. So we did our IVS measurement on the Davlin-1 molecule. I'm showing the ground state Raman here, just for reference, and the red is our excited state Raman spectrum, if you want to think of it like this. So what we find in good agreement with our calculations is indeed you see this cluster of modes around 600 range of wave numbers, which seem to be strongly coupled to our S1 state and therefore appearing in the IVS spectrum. And at least it gives some initial evidence that these calculated modes around these wave numbers are indeed present and they are coupled to the excited state. So that's very nice. So if we want to measure the triplet stellar populations, we use something else. And for that, we use transient EPR spectroscopy. And I won't go through it in too much detail, but the idea basically is if you have a molecule with this unpaired spins, a triplet excited state, when you put it in a magnetic field, through the Zeeman interaction, you sort of separate out those different sublevels depending on how the spins align with the implied field. And if you have sort of microwaves being injected into your EPR resonator, which are sort of tuned to be a frequency that's roughly equal to a spin transition, as you increase the field, when the sort of transition splitting becomes equal with that microwave energy, you drive, assuming you're having a sort of a non-Boltzmann population of these triplet sublevels, you drive transitions between them. And this manifests as emission or absorption of microwaves in the EPR spectrum that you detect. And what's quite nice is that the different triplet sublevel populations relative here will give you a different spectrum. And by simulating the spectrum, you can basically go back and work out what's your relative triplet sublevel populations. So working with Jean Gruner and Alberto Privatera, who's now in Florence, we did some EPR measurements on these Davlin-1 compounds. We get a nice intersystem crossing triplet with some emissive transitions on the low field side and absorptive on the high field side. And if you remember by theory, our collaborators predicted dominant coupling into TY, a little bit into TZ, and nothing into TX. And indeed, when we simulate our EPR spectrum, we see the same thing. We get dominant into TY, a little bit into TZ, nothing into TX. So I think it's a really nice way of experimentally confirming that our calculations are somewhat accurate. We can see the vibrations, and we can see their effect in the EPR spectrum, which seems to be consistent with what we think. And it's a very, very final thing, just a couple of slides. we thought, okay, well, we have this Dabner 1 molecule, which is a very classical material, which kind of means it doesn't work very well because it's one of the first ones that people came across. What people do is they take this core and they stick stuff on the outside. And I don't really know what that stuff is doing, but it seems to make it a much better molecule. It has much more efficient reverse intersystem crossing and works much better on an OLED. So it's all a bit of a work in progress. So what is adding the stuff doing? Does it change intersystem crossing mechanism like significantly, or is it just improving how efficient the same mechanism is? So we measured our transient EPR, well, IVS as well, but I won't show that. We measured transient EPR. Very similar spectrum. I mean, it's a bit more spectral broadening here, but otherwise, the simulation shows very, very similar triplet sublevel populations between Dabner 1 and the better one with all the stuff on the outside. Well, I haven't shown the IVS, but we see coupling to very, very different modes in that IVS spectrum. So I think what it's kind of telling us is probably what's going on, and we're still working on calculations to show this, is that when you add the stuff on the outside, it's still driving the population into the same triplet sublevels, the TY, seems to be the key one for mediating forward and reverse intersystem crossing. But somehow that new vibrational couplings are making it more efficient. So you're basically somehow improving that, and that's still a work in progress. So yeah, that's kind of, I think, quite a nice way we can basically combine experiment and theory and use it to provide really fundamental insights into how things like intersystem crossing work on organic semiconductors. Here we chose an OLED material, but I guess in theory it could work for many different things. With that, I probably overstayed my welcome. So I'd like to just acknowledge and thank the people involved in the work. So back in Cambridge, Sasha Snade did a lot of the IVS with me. And Richard Pren, who again supervised me during my PhD, which was some of the first things we saw on the triplets in OPV. We have theory collaborators in David Bergeron's group and Johan Livier's group in Belgium. For OGMAR and EPR, we have the group in Würzburg, Janine Gruner, Andreas, and Vladimir. And also in Oxford, Mosin and Alberto Privatera with William Moyes, who's the facility manager helping out. And then, yeah, for materials, I'd like to thank the group of Quinn Wynn in the UCSB, Feng Gao's group in Linköping, and Jun Yuan in Central South University. And yeah, for funding, I'd like to thank the Swedish Research Council, Linton and Alice Wallenberg Foundation for giving me money to do research, and back in Cambridge, the Leverhulme Trust for funding my position. So thanks for your attention. Happy to take any questions you might have.
Thanks. Just a reminder, if you have any questions, wait until the mic comes over. So the mic over to Mike, please.
Thank you so much. So I have a question coming from an inorganic semiconductor world about the energy gap law. So as an inorganic semiconductor physicist, of course we have the similar thing where, of course, all LEDs, etc., the external radiant efficiency decreases quite strongly with band gap. But there are engineering strategies to spatially separate electrons and holes on, quite small scales and decouple phonons from the carriers. You also mentioned this separation spatially of the HOMO and LUMO levels in the TDF molecules. Can you speak to any strategies there in trying to overcome the energy law for narrow bandgap emitters?
Yeah, so that was actually, there was a paper from the Cambridge group in Nature, I think, was it last year or the year before, that I was somewhat involved with. I wasn't the lead person at all. But they found basically what you said, which is in TADF molecules and some of the radical emitters, if you can separate the electron hole, basically, those high frequency modes, the CC stretches, are quite localized. And they no longer modulate both electron hole together and sort of couple to the excitonic transition. They kind of just modulate one or the other, and therefore they don't couple so strongly. And therefore, if they don't couple, they don't mediate non-radiative decay very well, and the PLQI goes up. So what you basically just described, I think, also applies to a degree to organics, and that's something that people are looking into. The problem with that is making something CT-like is you win in that way, but it also decreases the radiative rate, which kind of opposes any sort of reduction in the non-radiative rate, right? So it's quite a careful balancing act, and also means it doesn't absorb light very strongly, because the oscillator strength goes down, and it's unfortunately no good for an OPV. But it's definitely one tactic, and in the OLED world, where you don't need to absorb light strongly, it's very relevant. But I think for OPVs, maybe other things need to be thought of, which I don't know about. Otherwise, I'd be doing it. So, yeah. Thank you.
Any other questions from the floor? I have a couple. All right.
Okay.
So the transient EPR right at the end. Now you see a very similar polarization over the 3 triplet states.
Mhm.
I know you haven't finished the theory yet, but are you thinking it's the same symmetry of, like, it's a different set of vibrational frequencies, but is it the same symmetry of those modes?
I couldn't tell you.
Okay.
So our collaborator Johan is currently running the calculations, so I will defer my answer until I have such results. But yeah, it could be a possible thing. Yeah.
I have more, so you guys are gonna have to either. Sorry, I have to stand here. There we go, Riz.
Thanks for the nice talk. I have a question on the hybridization picture. So hybridization of the spin triplet CT states and the triplet on the isolated molecules. What is the role of exciton delocalization on the polymer chain? Because that's where you have more leverage for delocalization. So over like few tens of angstroms, because that's the distance.
So how would delocalization affect hybridization?
In my opinion, it would just not hybridize because...
Yeah, it should reduce electronic coupling because of greater spatial distance on average. And yeah, that's a good point. I mean, that's not something we considered, but for sure, maybe some of the polymers, for example, are more prone to delocalizing their holes and reduce hybridization. So, I mean, we saw a lot. We obviously had a fairly limited range of systems because time, we only do about 10 realistically, but we just see a lot of the PM6 PBDBT based polymers didn't show these mixing effects. Maybe the polar ones are more delocalized. That's wild speculation, of course, but it could be possible. Yeah.
So I have a related question. What does distance mean? Is it nuclear distances or what?
It's the average. Okay, again, it's a question for Davi more than me, but I think it's basically the average separation between the donor and acceptor. So what they do is they're based on, I think, some sort of NMR and some other stuff. They kind of can identify maybe the most light and also calculations, the most sort of favorable donor receptor conformations at the interface.
Okay.
So you may say my donor receptor alert you to pack in this way or that way or whatever because of energetics, and NMR can provide some sort of limitations, especially in the PM6Y6 case of how far fluorine atoms have to be from each other.
Right.
So you take that and then the model, they just pull it apart. They just increase the distance and see what happens.
Right.
So it's not reality, of course, but it's showing, if your electron sits and holds it further apart, maybe due to morphology, different interface packing, or on a molecule stacked further away, that's kind of what happens. So it's a toy model, but it can be quite informative.
Yep.
Mm-hmm.
Any other questions from the floor? I told you I have more. All right, I'll ask one last question. Okay. So you were talking about the triplet states in Y6 in your Nature paper, and you were talking about the TTA effects, and you were trying to work out where that's playing roles. Oh, sorry, the triplet effects.
Yep.
And looking at the fluence dependence. How similar was that to solar fluences?
So I think,
right?
So I think it's all approximate, of course. I think the lowest fluence is about 3 sun, and the highest one's about 15.
Okay,
which is just
crazy.
It's a tool to basically get. I mean, obviously, 15 sun is not relevant for solar fluences, but to see the mechanism, it's useful.
Okay. So with that, there's nothing left to do except we got one more. One more just jumping in.
Alex, thank you for the talk. It was great. What was the advantage of ISRS, is impulsive
vibration?
over FSRS, femtosecond stimulated Raman scattering?
Probably it's easier to do. And FSRS is I haven't done it, but I've heard it's a real pain. IVS, I mean, in the simplest sense, if you're just doing a 2-pulse measurement, you just excite your molecule with a very fast pump, and you get the most strong coupled to S1 because you're kind of exciting across the S0 S1 transition. You get the most, like a resonant Raman type measurement on S1 effectively. Just easier. Yeah.
For context, Armin's PhD is going to be using FSRS.
So I don't know. It's possible, but yeah, I mean, in our case, we didn't have the setup and it was easier. So.
Cool. All right. Well, there's nothing left to do except wish you the very worst of luck for the Ashes, and to thank you for your talk. So thank you very much.
Thank you.